Okay, fantastic. So welcome back to the lecture, and we had 1 week off for the reading week, and also we had an exam. So hopefully, which I have seen, by the way, that you have done an excellent job. I'm very happy of that. Now we will follow with the course which we stopped last time, which was solving Laplacian in the spherical coordinate. We did not complete that, and today we will continue with this, and we will try to complete that section as well. Okay, so I have taken a little bit of notes because usually I forget things about what we have done last time. So we started with the spherical coordinate, and we assumed that in the spherical coordinate that we had, of course, we have 3 parameters describing the space there, which is R, and then we have theta, and we had phi, and then in the spherical coordinate R, theta, and phi, we try to solve the Laplacian of phi, which here is R, phi, and R, theta, and phi equal to 0. And we try to solve this. Essentially, we started with the form of Laplacian, and then we did the separation of variables, and we got into, let's say, 3 different equations. So one essentially was the azimuthal part, which was e power of plus I and phi. And then the radial part was easy. So we say that it's r power of L, and then or r power of minus L plus 1, and L is positive integer. Here's what we got that. And then for the theta side, we got the following equation. We assume that we do the change of variables, and we got x equal to cosine of theta. And then by this change of variables, which we did it last time, we got into the following equation, which I think was the dx 1 minus x squared dx of I think we choose the function to be theta capital, if I remember well. So yes, was theta capital of x, and then plus L times L plus 1, and then we had minus m squared divided by 1 minus x squared, I think. Yes, was 1 minus x squared. And theta of x. Okay, so that was what we got last time. And then we assume that we are solving the problem for the case of m equal, we do have Nazanin back. So we do have, we consider that m is equal to 0. And then we deal with this equation, which was d dx of 1 minus x squared d dx of theta plus L times L plus 1 of theta equal to 0. And we say that this is a second order differential equation, and you can use the Frobenius technique and solving the equation. As soon as L is integer, the series is bounded. Okay, So just to recall, then if you want to expand the equation, if you want to do the expansion, let's do the expansion of the differential equation and finding out the orders, and then we can look into understanding the point of singularities, and also a little bit better about the series, because that was the part that last time I went very quickly because I want to just introduce you Legendre polynomial. So essentially here, if you do the expansion, then you will get 1 minus x squared d to dx squared of theta, and then we get minus 2x d dx of theta, and then plus L times L plus 1 of theta equal to 0. Then you divide both sides with 1 minus x squared, then you will get d2 dx squared of theta minus 2x divided by 1 minus x squared d dx of theta plus L times L plus 1 of 1 minus x squared theta equal to 0. And recall that the domain that we do have is minus 1 to 1, because theta is belonging to 0 and pi. Therefore, cosine of theta is changing from minus 1 to plus 1. Okay, so that immediately recall that it's not exactly the solution, but it reminds us of the Legendre polynomials, because last time we solved the Legendre, and we realized that they form orthogonal basis and complete basis in interval of plus 1 and minus 1. So that was essentially the point, and without going into the details, I told you that this is Legendre polynomial. Look at the point here. So in the dominators, 1 minus x squared is appearing. So, and this is singular. Where they are singular? At x equal to plus 1 and minus 1. Okay. And the type of singularity is power of 1, so is a regular singularity, is not essential singularity. And we say that even without considering this, simply what we can do is assuming that theta can be expanded in terms of x power of alpha summation of an x power of n, which n is changing from 0 to infinity, and then you can find a solution. Okay. So indeed, you will get a relationship among an plus 1, an plus 2, and etc., which essentially is between an and an plus 2. Okay. So if you look at the series will be infinite number. Okay, it's not bounded. So the number of series that you do have, the number of ans that you do have, essentially n goes to infinity, so it's not bounded. If the series is not bounded and x value takes the value of plus 1 or minus 1, then you know that the series may be divergent. Okay, this is the first form that you do have it for finding the condition of converging a series. All right. So this poses a question, a serious question, that what is happening if x takes the value of 1 or plus or minus 1? Then if the number of elements of the series is unbounded, then the series may be divergent. So the only condition that you can apply here that the results in a converging series is that the number of series should be bounded. And then from this relation, you will get that L is a positive integer. So it means that the number of elements that you do have for the series is bounded. And you can look at the value, what is happening for L equal to 0. For L equal to 0, then theta x is equal to 1. And for L equal to 1, theta x will be equal to x. For L equal to 2, theta x will be equal to, I think it was 1/2 of 3x squared minus 1. Okay, so that recalls that this condition that you do have on L will create you solutions for these differential equation, which they are identical to Legendre polynomial that you do have it. Okay, so therefore, theta can be labeled by L, and we agree that the solution that we do have for this differential equation essentially is PL of x, which is the Legendre polynomial. Recall, this is not a normalized one. It's a non-normalized Legendre polynomial, the one that physicists they use. All right. If you recall, also, we say that Legendre polynomials, they are orthogonal in that one. They are orthogonal in the interval of -1 to +1. So PL of x, PL prime of x, dx is equal to, what was it? Was 2 divided by, I think it was, yes, 2 divided by 2L plus 1 of delta of L prime. Okay. But definitely we can prove that they are orthogonal from the differential equation, because it is some form of a Sturm-Liouville differential equation. So let's try with that. I will go, let's go with, let's go with this form of differential equation, which is dx of 1 minus x squared dx, and we know that the solution, they are now PL of x plus L times L plus 1 of PL of x equal to 0. All right. Now I want to prove that they are orthogonal to each other. So what I do, I multiply both sides by PL prime of x, and then I will do the integral in the interval of -1 to +1. Let's do that. So the result will be integral of dx from -1 to +1, PL prime of x, then dx of 1 minus x squared dx of PL plus L times L plus 1, integral of dx minus 1 to +1 of PL prime of x, PL of x, which is equal to 0. So we can use the by part here, integral. This is look like du, and this is look like v. Then the result will be uv minus u dv. All right. So the result of this will be integral of -1 to +1 dx. When I say is du, I mean the entire of this is du. So that will be PL prime of x, 1 minus x squared dx of PL of x from the interval of -1 to +1. All right. minus 1 to plus 1 dx. It will be u dv, so 1 minus x squared dpl dx times dpl prime dx plus L times L plus 1 integral of minus 1 to plus 1 dx p L prime of x p L of x equal to 0. Do you agree, guys? So what I have done, just I used the by part and then I expanded the first term. What is the result of the first term out of the 3? This one. Gavin? We have to substitute plus 1 and minus 1, right? True. So what is up? Yeah, exactly, because that term will be 0 at plus 1 and minus 1. And we know that the rest is a polynomial, so definitely it has a value. So that will be a 0. Then what we will get is minus integral of minus 1 to plus 1 dx 1 minus x squared dpl dx dpl prime dx plus L plus 1 integral of minus 1 to plus 1 dx p L x p L of x equal to 0. All right. We can do the same calculation when the differential equation is written, when this differential equation is written for L prime. So when it is written for d dx of 1 minus x squared d dx of p L prime of x. Okay, that's also again a Legendre differential equation, but what we have to do, we have to substitute L with L prime in order to satisfy the differential equation. So that will be plus L prime plus 1 p L prime x equal to 0. All right, so it's identical. Then you can multiply both sides by p L of x, and again integral in the interval of minus 1 to plus 1 dx. What you will get exactly the same expression as this one. The only difference is that any L is replaced by L prime and any L prime is replaced by L. So what we will get minus integral of minus 1 to plus 1 dx 1 minus x squared dp L prime dx dpl dx plus L prime times L prime plus 1 integral of minus 1 to plus 1 pl x pl prime of x equal to 0. Do you agree? Now we can subtract the two equations. What the first term goes away, then finally what we will get this expression. L times L plus 1 minus L prime plus 1 integral of minus 1 to plus 1 dx pl of x pl prime of x equal to 0. True? If L is not equal to L prime, then the term inside of bracket is not equal to 0. So therefore, what we should know in order to satisfy this expression is PLX, PL prime of X is equal to 0. So whenever L and L prime, they are different, then the result will be equal to 0. So they are orthogonal. Essentially, we know that because we proved already that these polynomial series all they provide a complete basis, essentially, and orthogonal. And from the expression that we had previously, we can also get the results that we discussed. So essentially, 1 minus 1 to plus 1 of PL of X, PL prime of X is equal to 2 divided by 2L plus 1 of delta of L prime. Okay. So that was the entire of this expression that we solved. Now is for the case that m is equal to 0. When m is equal to 0, then we know the solution for theta is PL of cosine of theta, and solution for the radial part is given by either r power of L or r power of minus L plus 1. Okay? Is that clear? So potential, if the potential is cylindrical, spherical symmetry, then m is equal to 0. Therefore, the solution that we do have, it's PL times either one of these two terms, okay, or the sum of the two, which only can be labeled by one parameter, which is L, and nothing else. So essentially, the solution will be potential of R, theta, and phi. By the way, is not anymore function of phi, because we say that it holds the spherical symmetry, which means that if you rotate it, you don't see any changes. Then the solution will be given by summation of on L, which is changing from 0 to infinity, of either AL times R power of L or BL R power of minus L, which I would prefer to write it in different form, B divided by R power of L plus 1 times PL cosine of theta. Clear? So if you do a full rotation and the system is not changing by applying any rotation, for example, if you take this cup, sorry, this is not a good example because it's edges, but assuming that these look like a round glass, okay? So if I hold this round glass and is in empty space, nothing is there which is breaking the symmetry. If I choose the axis of Z like this, okay, around the Z axis, it's cylindrical symmetry. So it doesn't matter if you are here or here or here, then the potential will be identical. There is no way that you can distinguish the space by rotating, okay? So it's rotationally invariant along the Z axis. Then you expect that the potential will not be depending on the phi azimuth angle. Clear? Good? So fantastic. So in this case, the only functionality that you do have for this, let's say, cup of glass is only functionality along R or theta, because we know that if you move the theta like this, right, you will see this glass from different angle. So definitely the potential will change. Now this can be kept at the constant potential or with a certain charge distribution, but this is exactly the situation that we are talking about. Okay, fantastic. So should we solve a problem based on that? For a system which is cylindrical symmetry. Assuming that I have a sphere which this sphere, just don't get angry, guys. That was, it reminds you of something. This is the sphere. And I kept, this one has a potential of V0 and the lower in the potential of minus V0. Right? You solved, this was your midterm exam, right? And I asked you to find the potential anywhere outside. Find the potential here, r, theta, and phi. I gave it to you, and you solved it from completely different approach, which the approach was using the green function, right? That was what we learned during the previous lectures. But now we are solving it from a different approach. What is our approach? Is solving from Laplace equation. Outside of the space. First of all, the question is that where do you want to find the solution? Outside of the space. We may have, and we may look for solution inside of the sphere as well. Okay, we can go either inside or outside. Let's solve it for outside first. Outside the sphere, which north and south hemisphere spheres are kept at potential of V0 and minus V0 respectively. And later on, we will solve it what is happening inside of that. So outside of this, is there any charges in the outer space? There is no charge. What you have to solve to find the potential is solving Laplacian of phi equal to 0. All right? Now, this is a perfect sphere. Do you expect the potential will be depending on the azimuthal angle? No. The potential is not a function of azimuthal angle. So, due to the symmetry, that we do have, the potential is not depending on phi. So, phi r theta and phi will be equal to phi of r theta and phi plus any delta phi, any rotation that you do have. Okay? Or phi prime, or phi 0, or phi 1, whatever you want. So therefore, the potential that we do have, r and theta, will be given by, as we solve right now, it will be given by L equal to 0 to infinity of a L r plus of r power of L plus BL divided by r power of L plus 1 PL of cosine of theta. What we need to do is just choosing a coordinate that we are looking for. So only choosing a direction of z. When you choose that, then everything is fine. We cannot have other symmetry because the north hemisphere is kept at the potential of V0 and the south hemisphere is kept at the potential of minus V0. All right, so that's a point. So there is an axis which is defining what is happening, what is the orientation of the sphere, and we kept that that axis to be z. Okay, and then this angle is theta. And the distance, of course, is given by r. Now, that's the potential. What it will be the potential at infinity? What are the boundary conditions? One is at the infinity, the other one is at the surface of the sphere. So we have two boundary conditions, so the two regions essentially. R goes to infinity, and R tends to be A, which is A is the radius of the sphere. Okay? At infinity, R goes to infinity. What do you expect for the potential?
Should become 0.
Exactly, should be bounded essentially, or should be equal to 0, because it's a localized charge or localized potential, and then when you go there, it should be 0. So phi should tend to be 0. Then it means that, look at the power series. R is equal to, because L is equal to 0, right? To 0 to infinity. So whatever happens here, R power, the positive power of R is not, they are not allowed. So definitely AL is equal to 0. Okay? Then the solution now that we are looking for is phi of R and theta due to the first boundary condition that we assume, which is potential at infinity, now is reduced to be summation of L equal to 0 to infinity of BL divided by R power of L plus 1. Okay? PL cosine of theta. Good? Now, in order to find out the value of BL, what we have to do, we have to look at the other boundary condition, which is what is happening at the surface of the sphere. So it means that look for the potential at R equal to A. Let me write it explicitly. At R equal to A, and any theta value. Okay? Then what it will happen, the summation that we do have will be now reduced to summation of L equal to 0 to infinity, BL A power of L plus 1, PL of cosine of theta. Okay? This is what we have. What are we going to find out, guys? What are we looking for? BL. So in order to find BL, we have to multiply both sides by PL prime cosine of theta, then doing the integration, which is D cosine of theta. And from interval of -1 to +1, okay? If you do so, then you will get let's do that. So integral of -1 to +1, D cosine of theta, phi of R equal to A and theta. For different theta, we have to solve it because you will see the value will be changing. And then other side will be L equal to 0 to infinity of BL AL plus 1, and then integral of D cosine of theta. There's a PL prime also here, cosine of theta. PL of cosine of theta, PL prime of cosine of theta, from -1 to +1. What is the value of this, guys?
L over whatever +1 delta function, or Kronecker delta?
Yeah, it was 2 divided by 2L plus 1, if I recall well. I want to be honest with you, I will give you this expression because I don't remember. I have to drive it from the beginning. Delta of L and L prime. So I think that should be, yes, that is exactly the expression. And just to tell, I have a cheating sheet. So I have for myself also, either I have to drive that or I have to memorize it. Good. So okay, so we get a delta of course, delta Kronecker, and the summation of the delta Kronecker will be 0 everywhere when L is not equal to L prime, and else it will be equal to 1. So then therefore that will get B L prime divided the A power of L prime plus 1. And then we will get 2 divided by 2L prime plus 1. All right. Good. From here, then we got the value for BL prime, which is 2L prime plus 1 divided by 2. Then we do have A power of L prime plus 1. Then integral of -1 to +1 of d cosine of theta PL prime cosine of theta phi at r equal to a and any value of theta. Agreed? Good. So now is a fun part. The potential. Now we have to express it in terms of cosine of theta, right? So the potential is positive V0 and negative V0 for the north and south hemisphere. So what is happening if you assume that this is the theta that you do have, with theta is changing from the theta is changing from 0, which means that the cosine of theta is changing from +1, and when theta is equal to pi, then cosine of theta will be -1, right? So and of course, definitely at the equator, which we do have cosine of theta to be equal to 0, then the jump will happen. So this value that we do have is a cosine of theta. So for the, let's say, 0 to +1, which is associated to the north hemisphere, you have a positive V0. And for the south hemisphere is equal to negative V0. You agree? Then means that 2L prime plus 1 divided by 2AL prime plus 1, that integral will break down into 2 different integrals. One is integral of -1 to +1, sorry, -1 to 0 of d cosine of theta, PL L prime cosine of theta, and the potential for this range will be negative V0 plus integral of 0 to +1 of d cosine of theta, PL prime, sorry, of cosine of theta times V0. All right. So far, so good, right? Okay, fantastic. Then we can simplify this further. We will get I will do the change of variable, so it will be 2L prime plus 1 divided by 2al prime plus 1. Then this expression will be cosine of theta is x, essentially that will be x. So it will be v0 factor out. That will be a negative sign. 0 to 1 of dx p L prime of minus x. Okay, and the other term will be integral of 0 to 1 of dx p L prime of x. Okay. So instead of cosine of theta, I place x, which doesn't change because I already changed the argument. There is a d cosine of theta. And what I have done for the first term, I swap x with minus x. So dx will be replaced by minus dx, which the interval will be swapped. You will get another minus sign, which they will cancel out each other. And then inside of the Legendre polynomial, you will get minus x because we already changed x to minus x. And then the other term is the same. Okay. Do you remember Legendre polynomials? Where they would look like? The first one was 1. The 0 one was 1. P1 was x. P2 will start with x power of 2, and it was something like that. P3 starts with x power of 3, and then you have an x, which was something like that. So you see that, you will see that for odd and even values, either PL, they will be an even function or odd function. Okay. So what does it mean that I can simplify this expression? Will be 0 to 1 of dx p L prime of minus x plus p L prime of x. All right. So if the function is even, that will be 2 times the value that you are expecting. If the function is odd, then that will be equal to 0. Okay, twice of integral of 0 to 1 dx pl of x for even function, which means that also is even index, and that will be equal to 0 when it is odd function. So then I will get the expression for b L prime, which is, I know that L prime is now even. Okay. Two goes away, then I get 2 L prime plus 1 b0 integral of 0 to 1 dx p L of x, which now we will look for that. And then I have a power of L prime plus 1. Okay, so let me look at the expression that you may have it in your book. Very likely you should have it in your book. I cannot find it. Anyway. So the expression is given, and then you will get the final results essentially, okay, which will be what is going on with the potential of r, theta, and phi, or let's say.
Should there be a 2 in the front?
The 2 goes away with this one.
Sorry, where? Oh, okay, thank you.
The 2 goes away with that one. So it will be summation of L equal to 0 to infinity of the BL values, which we found it here. So it will be 2L plus 1, V0, that value, which I don't know what is the value. Then it will be A divided by R power of L plus 1. Let's call this value N, okay, which is this value. NL, of course. And then you have PL of cosine of theta. Okay. Clear? Let me just check out. So that is -1 to +1. Okay, okay. That's P1. It's P0. P2 will be like that. And -x will be identical to x1. Okay, okay. Double check it if maybe I have done a minus sign mistake. I feel that there's a minus sign mistake somewhere. Maybe odd values, they will remain, and even value, they will be canceling out each other. But it's based on the symmetry that you have to look for, and looking for the odd and even function. So far, so good. Now we can go and try to solve another problem, just to understand that the physics gets sometimes very complicated, and you have to handle the things very, very carefully. Do you have any questions, guys? You solve this problem in a different way, right? Which was there are multiple ways to solve a physics problem. Now let's assume another physical system. Assuming that you have a cone, look like one of those metallic cones that we can sometimes find it. So you have the cone, and this is a metallic cone, and we kept it as certain potential. Okay. I choose my coordinates such a way that it will be aligned like this. Okay, so that is a z-axis. It's way easier. You can choose it in any direction that you want, but this is the best way to solve it. And then differently, and the cone goes to infinity, by the way, is a metallic one. And I kept it in a certain potential of phi 0. The entire cone. Now I'm asking you, I have forgotten something else. Okay, let's go back to the previous problem. My apologies. We will come back to this problem and we will solve it. Assuming the previous problem. So in the previous problem, we looked for the potential outside of the sphere. And we kept the potential at +0, V0, and that one minus V0. And we say that find the potential anywhere outside of the sphere. Now the question that I'm asking you is completely inverted, and I will say that what is happening with the potential inside of the sphere? let's solve it. All right. Find the potential inside the sphere. Mathematically means that for R smaller than A. Let's find a solution for that. Again, going back to the same physics, inside of the sphere, you cannot distinguish the azimuthal orientation. And assuming that we choose the Z direction along this, then the only dependency that you do have is the distance from the origin and also what is going on with the theta angle. So then phi again is given by R and theta. Then the solution will be given by L from 0 to infinity of AL R power of L plus BL divided by R power of L plus 1 PL of cosine of theta. Now, what are the conditions that we do have for potential? Let me ask someone like Melika.
Yeah. So you ask, what are the conditions you have for potential?
Yes, what we have to do, because we have two parameters of AL and BL, and we have to determine them, right? What are the conditions that we have to apply to phi in order to determine AL and BL?
Yeah. Okay. We need to know what happened to potential when R goes to 0.
Excellent. When R goes to 0, what do you expect for the potential? To be confined, right?
Yeah.
Phi should be converging, right? And what is the other condition that we do have? At the
What
surface.
happened? Yeah.
Exactly. At R goes to A, phi must be given by the same expression.
Yeah.
The same expression, which means that at between theta equal to 0 and pi divided by 2 should be V0, and pi divided by 2 to pi should be minus V0. Excellent. Thank you, Melika. So using the first condition that we do have, what we will get? Using the first condition. If R goes to 0, we have two terms that they have functionality of R. They are depending on R. Is R power of L or R power of minus L minus 1. So definitely at R equal to 0, that term will diverge. So therefore, BL should be equal to 0. Okay. Therefore, using the first condition, we reduce the form of potential to be this one, summation of L equal to 0 to infinity of AL R power of L PL cosine of theta. All right. And now we have to find what is going on with AL. Okay, what's going on with AL? At phi R equal to A and any theta value, then we do have this, which is L equal to 0 to infinity AL A power of L PL of cosine of theta. Therefore, AL is given by L plus 1 divided by 2 A power of minus L, then integral of d cosine of theta PL of cosine of theta, and then the same expression that we had phi of R equal to A and theta from -1 to +1. Okay. So from here, we can calculate what is going on with AL, which is exactly 2L plus 1 divided by 2, a power of -L. And this is exactly the same expression that we had. So it will be 2 goes away, and that will be NL. And you have to check it if L will be only even one or odd one. One of these two will remain because you have to look at the symmetry. So replacing inside of the expression, we will get the phi of r and theta equal to summation of L equal to 0, infinity. Now I'm replacing AL, it will be 2L plus 1, and then NL, which NL is an expression, you will find it out, what's going on, and poses a condition and the value of L as well to be odd one or even one. And then I got R power of L, and I get A power of -L. So it will be R divided by A power of L, PL of cosine of theta. Okay. So that is the case when R is smaller than A. For R greater than A, we find similar expression. Just let's visit it again. It was 2L plus 1 and L. I think we had A divided by R power of L plus 1, PL cosine of theta. Good. That I think, let me double check it, guys, but I think, yes, that's the expression. There was a V0 as well here. It was a V0. Okay. Yeah. So inside of the sphere or outside of the sphere, you will get dependency on theta to be identical. That's the point. If we look at the expression on theta, you will see that the expression on theta is only given by this value. So if the sphere is here, we plus V and minus V, along this direction, right, along the theta, you have the same expression, only the radius will be different. When the radius will be different, then the potential will be different. So the functionality of on theta will be given by Legendre polynomial, which is PL of cosine of theta. I will come back to this as with another example, because that's really a consequence of the symmetry that you are expecting. So the potential of V0 and plus and minus V0, which you choose your coordinate axis to be along Z, right? And along, let's say, North Pole to the South Pole, or South Pole to the North Pole, it gives you a condition that you will find out what is happening with dependency on the theta. If you are inside of the sphere, you are expecting that the potential, when you go to the radius of 0, the r equal to 0, the potential will be bounded by 0. When you are going to infinity, then also the dependency is such a way that the potential at infinity will be 0 as well. Okay? You have to pick up the right terms, not those converging one and diverging one, only the converging one. When you are at infinity, the potential, the highest order, we have to look at the value. I believe that it should be odd value, by the way, for the L, because of the physics that I see. So in the calculation that I say in this reducing the values, I think I did a mistake. So it should be an odd function. So if you go to infinity, I'm expecting the highest order. So will be L equal to 1. Okay, that is what I'm expecting. Because if L equal to 1, then the potential goes to be 1 divided by r power of 2, which is look like a dipole. So if you go to infinity, you will see it as a dipole moment because it's a potential of P plus and negative one together. Okay, we can see that as well here if we assume that the point of observation is along the z direction. So this is the sphere that we do have. That side is minus v0, that side is plus v0. But instead of going anywhere here, now I am looking at the point I'm looking for the potential anywhere along the z-axis. Okay, anywhere along the z-axis means that theta is equal to 0. When theta is equal to 0, then this dependency will be equal to 1, right? Because this is what we learned, that PL of any value of 1 always is equal to 1. Then phi, r, and theta equal to 0 will be given by summation of L equal to 0 to infinity of V0 and L to L plus 1 of A divided by R power of L plus 1. Then if I go to infinity, which means that R tends to be really large, then let's be precise, R is way greater than A, then I see the entire sphere as a dipole. When I see as a dipole, the potential for a dipole will be 1 divided by R power of 2. Okay, if you do the calculation for a dipole, the potential for a dipole will be 1 divided by R power of 2, and the electric field will be 1 divided by R power of 3. Okay, therefore, you will see that exactly from this expression that L will be either 1, it will be L equal to 1, 3, 5, 7, and etc. because that's the odd functions that we are having it. And then if you substitute it here, you will see that it happens with R power of 2, R power of 4, R power of 6, and etc. So you will see that the contribution from the dipole will be maximized. Okay. So there are a lot of beautiful physics here that someone can look into it. Now, let me give you another problem. The potential on the surface of the sphere, now it's look like having a sudden jump of plus V0 to minus V0. Now I am giving you another problem which the potential on the surface of the sphere has a specific functionality. So the functionality that on the surface of the sphere for the potential is phi at r equal to a and any theta, and phi is given by cosine of theta. So it means that at the cosine of theta times V0, let's look for the dimensionality because I have to have the proper dimensionality. Phi at the surface of the sphere A is equal to V0 cosine of theta. It's very similar to the previous problem, right? Because when theta is equal to 0, that will be here plus V0. When theta is equal to pi, the potential here will be minus V0. And what is happening at the equator will be 0 potential. And what is happening at the angle of pi divided by 4, that will be V0 divided by square root of 2. And here it will be V0 with the negative sign divided by square root of 2. Okay. Now I'm asking you find the potential anywhere outside of the sphere. or inside. It's depending on you. Okay. Find the potential in the space for r greater than a or for r below a. Can you solve it, guys? I will pause the video and I will give you 5 minutes to solve it. Let's go. So the key point for that is cosine of theta, or phi at, we say that phi at a equal at r equal to a is equal to v0 cosine of theta. So essentially is v0 p1 of cosine of theta. So the system has a cylindrical symmetry. Based on the discussion that we had, the potential will be only function of theta and r. So therefore, I am expecting that the potential r and theta will be given by summation of L from 0 to infinity of AL r power of L plus BL divided by r power of L plus 1 times PL cosine of theta. All right. So we have two conditions where we want to solve the problem: r greater than a or r below a. So r greater than a. Let's solve this again. So then, therefore, AL will be equal to 0 because when r goes to infinity, that should be limited. Then potential should go to 0. Therefore, we reduce that to be summation of L from 0 to infinity of BL divided by r power of L plus 1, PL of cosine of theta. And that's the potential for r and theta. And now we say that we apply the second condition that at r equal to a, then the potential should be given by V0 cosine of theta, which is V0 P1 of cosine of theta. Good. So therefore, we are substituting it here. So it will be V0 P1 of cosine of theta is equal to summation of L equal to 0 to infinity BL r power of L plus 1 PL cosine of theta. And I know that PLs, they are orthogonal to each other. So it means that it looks like having a vector in one side to be a coefficient of I hat. And from the other side, we don't know what is the coefficient of I hat, what is the coefficient of J hat, what is the coefficient of K hat, or what's the coefficient of T hat. But we know that I, J, K, T hat, they are orthogonal to each other. So definitely, we know that the only term which is kept here is L equal to 1. And all of them, they will be 0. Or if you want to do it more formally, you multiply both sides by PL prime, taking the integral, and then you will see from this side that L prime is not 0 when A is equal to 1, else it will be 0, the integral. Okay, so from this relationship, what you will get is BL or B1 divided by A power of 2 is equal to V0. Then B1 is equal to V0 times A power of 2. Therefore, the potential that we are expecting for outer region is summation of L equal to 0 to infinity of V0. Yeah, let's keep it like that way. V0 A divided by R power of 2 of cosine of theta. in a similar fashion, you can prove it for what is going on inside of the sphere. That is for r greater than or equal to a. For inside of the sphere, that will be v0 r divided by a cosine of theta. All right. Clear, Gavin? Perfect. I can give you also more complicated situation. The potential on the surface of the surface, I can give you also potential, or I can give you even the charge density, guys. Because from the charge density also you can look at the derivative of the potential, right? That's the boundary condition that you have to apply. So electric field, normal of the electric field is the charge distribution that you know. And what is the normal of the electric field is the derivative of potential, okay, along the radial direction. Anyway, so I can give you even more complicated one. I say that, oh, the potential is given by 1 divided by, I don't know, sine square of theta, or 3 cosine square minus 1. This is the potential on the surface. And then I will ask you to solve it. Cosine theta minus 1. The key point here is the same. This is P2 of cosine of theta. So the only term that will remain is the L equal to 2 term. So remember, whatever is the form of the potential, it seems that is imprinted in the space. Okay? So if the potential has, let's say, cosine theta functionality, the form of the potential will propagate in the space as well. And that's really, really important that you feel. It seems that it's coming from some sort of continuity that you do have. Fantastic. Okay, now let's go back to let's go to the question that I posed, and now we want to solve another problem. So use the completeness and orthogonality of the functions in order to find out what's going on with the elements that they play a role in the potentials that you are looking for. Now let's go and look at the problem that I just described to you. Is we do have a cone of metal, and we choose the coordinates such a way that this is the z-axis. Then the opening angle is about beta. And now this is kept at a certain potential, let's say at potential of 0. All right. So potential at any value but theta equal to beta is equal to 0. Now we are asking you what's going on with potential inside of this region. Okay. So we do have a cone, guys, like ice cream cone, which is metallic one. And we keep the ice cream cone at a certain potential of 0. Now I'm asking what is going on inside. Find me the potential inside of that. Or you can keep it at a certain potential of V0. It's up to you. It's completely up to you. Okay? So, in a what you need to solve is solving the Laplace equation again. Which coordinate we should solve? Either you can solve it in cylindrical coordinate or you can solve it in spherical coordinate. Of course, Cartesian always is there, but it doesn't hold the symmetry that you are looking for. The symmetry is azimuthal symmetry, definitely. That's the reason that I say that you can go with spherical or with a cylindrical one. If you go with cylindrical, it gets very, very complicated because there will be a coupling between Z and rho, and it's not pleasant to solve. So the best coordinate to solve this problem is spherical one. Spherical coordinates. And since the system is cylindrical symmetry, then I'm expecting that there will be no dependency on phi. So if you rotate it, it looks like a cone. If you rotate it, nothing will change. So based on the discussion that previously we had, M should be equal to 0. M should be equal to 0. So there is no functionality on that. What about R? The radial part again will be given by R power of L or R power of minus L minus 1. Or let's go in this way. Okay, that's the radial part. The azimuthal part is the theta part is a little bit more complicated than we thought. So going back to the differential equation that we had previously, it was d dx, which x was chosen to be cosine of theta, and mx was equal to 0. Then we had 1 minus x squared of d dx of the theta part, essentially, plus L times L plus 1 of theta equal to 0. This is what we had. All right. And we had to solve this equation. So, and previously we say that the solution of the theta is PL of cosine of theta, or PL of x. That was what we previously had. Here, the situation will be a little bit different. Where we did the expansions, do you remember? I mean, previously, when we deal with this equation, we say that we have access to the entire space, which was -1 and +1. Do you recall that? Guys, do you agree? Perfect. So we had access to the entire space. So then we were allowed to consider the theta of x is expanded in terms of x power of alpha, summation of an x power of alpha, n start from 0 to infinity. And we say that in order to have the series to be bounded, then an should be bounded as well, in order to have the series to be converging, so n should be bounded. Now there is a problem here, which we may not be able to use the same expressions. Anyone having a thought why we may not be able, or we are not allowed to use these expansions? These expansions happens around which point? X equal to 0, right? But right now, for this geometry that we do we have access to x equal to 0? No, we don't have access to x equal to 0, because x now is bounded by 1, let's say, sorry, let's write it in a different way. X is bounded by 1 and cosine of beta, because the opening angle is about beta, and beta is below pi divided by 2. Okay, so that is our space. So since this expansion happens around x equal to 0, we are not allowed to use that series expansion. What we have to do? We have to do the expansion around x equal to 1, because that is included in the geometry that we do have. Clear? let's do a little bit of cheating. We don't like to do the expansion around x equal to 1. You can do that, no problem at all. Let's rewrite the equation with a new variable. What is the new variable that we do have? I will define zeta. I'm going with what is the notation in your book, which is 1 divided by 2 of x minus 1 minus x or x minus 1. God, I think it was, let's see, is the cosine of beta. So we want to go with a positive one. So I will go with 1 minus x. Okay. 1 minus x. Okay. And then we will rewrite the above expression. So now theta is, which previously was function of x, now is a function of zeta. Okay? Because I'm doing the change of variable. I'm changing x to zeta. Okay? Is it clear, guys? Should I go with u? Is easier or y? Okay. So so I have to change the differential equation, which is d dx of 1 minus x squared of d dx of theta of now it's a function of zeta plus L plus 1 of theta of zeta equal to 0. 1 minus x squared, so 1x, let's find x from this expression will be 1 minus 2 zeta. Okay. Then you can replace it here. I will get 1 minus 2 zeta power of 2. And then I have to do the change of variable as well here. So let's do the entire of this calculation. It will be, the first term would be d theta dx. Now it will change to be d theta d zeta dx, which is d zeta dx will be minus 1/2 d theta d zeta. All right, guys. Okay. So let's 1 minus x squared will be 1 minus 2 zeta power of 2. Check it out because I'm doing mistakes and when I'm not in front of whiteboard. That will be 1 minus 4 zeta plus 4 zeta squared. That will be plus 4 zeta minus 4 zeta squared. So that will be d dx, which will be d zeta dx d zeta, which will be minus 1/2 of d zeta. So the entire of the expression in above will be 1 minus 1/2 of d zeta. Then that expression will be 4 will be factored out, zeta will be factored out, it will be 1 minus zeta. Then I have 1/2 with a negative sign from the derivative, d zeta of theta plus L times L plus 1 of theta of zeta equal to 0. 4 goes away with that one, minus sign will go away, so it will be d zeta of zeta times 1 minus zeta d zeta of theta of zeta plus L plus 1 of theta equal to 0. Remember that the change of variable was 1/2 of 1 minus x. Okay, I got this differential equation. Now, with this change of variable, remember, x was bounded by 1 and cosine of beta, and now zeta is bounded by 1/2 of 1 minus cosine of beta, and that will be 0. Now 0 is included in the domain for this differential equation. All right, that was the trick, essentially. It's a second order differential equation. You can expand it. You can do the expansion, and essentially theta of zeta will be again given by zeta power of alpha summation of an zeta power of n changing from 0 to infinity. Replace it there. Okay, you will get Legendre functions, which is given by p nu of x, essentially, which x means that value, by the way, guys. You have to change the variable. And what is new, because previously we assumed that that is given by L times L plus 1, because the series should be bounded. If you remember, we say that at x equal to 1 and minus 1, the series should be converging. So that pose a condition that L should be an integer quantity. But here, there is no condition like that anymore, because the differential equation is different completely. But what you will get as a result, it will be a Legendre polynomial, a Legendre function. But instead of L, you will have nu as a parameter in the calculation. It's not anymore integer. Okay, so that will be the p nu of cosine of theta as the solution to the theta part. So now what do we have as radial 1 r power of nu, or 1 divided by r power of nu plus 1 times p nu of cosine of theta. That will be the solution. And recall that nu is not necessarily an integer number quantity. Okay, that was the tricky part. That was the reason that I started from Legendre polynomials, and I described to you why we get Legendre polynomials, because of the truncation, because the series should be converging, and the series will not be converging at x equal to plus and minus 1 if you cover the entire space, unless the series is bounded. But here the situation is very different. You are covering the x equal to 1 only, okay, and the opening angles. You are not covering x equal to 0, so you have to do the change of variable. As a consequence, since the space is truncated, you don't have access to all theta from 0 to pi to 1 pi, then you will have a bond on the let's say the integer that you introduce to the quantity, and is not anymore integer, is a real quantity. So nu here is a real quantity, and we will discuss about that, what is the functionality and how we can find the new value. Okay, so I think I see from the face of you guys that you are a little bit tired. Let's see each other in 15 minutes. Okay. take 15 minutes off. At 4:30, I will see you. So hope that you had a nice break. Now we are coming back to the problem that we had, and we found a solution in general for that explicit problem that we had, which was a cone with an opening angle of beta, and we realized by change of variables, we understand that that is given by Legendre polynomial, but however, the index is not anymore integer. So we got the solution for the potential then to be r and phi, r and theta, to be summation of nu. Then we had a r power of nu plus b nu divided by r power of nu plus 1 p nu of cosine of theta. And remember, the problem was a cone which was kept at a certain potential. Let's say for simplicity, we kept at a potential of 0. And the condition that we do have is that if we assume that for the internal, and we are looking for finding the potential here, and we assume that if you go to infinity, definitely the potential will be going to be 0. So at r going to infinity, then the potential should be bounded essentially. So then means that the first term, no, sorry, my bad. We don't have any condition on the infinity side. My bad, because if we have infinity, that's a problem. So the condition that we do have is when r goes to 0, then the potential is bounded. So it means that because we are including the origin, right? So when we include the origin, it means that r goes to 0, then the potential should be also going to 0. Therefore, only a new term will remain. So b nu will be 0. So the potential will be reduced to summation of nu. Then we do have a nu, r power of nu, p nu of cosine of theta. And we know that for any r values, and theta equal to beta, which is the opening angle here, the potential should be equal to 0. Should be equal to 0. So what does it mean? That it will be a nu for any r value, arbitrary, then p nu of cosine of beta should be equal to 0. What does it mean? That independent of the r, that part for any cosine of beta should be equal to 0. So it means that p nu of cosine of beta should be equal to 0. Okay. So what does it mean? Remember, nu is not integer anymore, by the way. There is a condition here. What the condition pose? What it will be limited by this condition? Let me say in this way. Can someone say microphone on?
And we need to like define something for new for
Exactly. New will be defined. Will be defined. So what does it mean that among the Legendre polynomials, those will remain which the the value of the Legendre polynomial at that given point is 0. That's all. Right? So cosine of theta, cosine of beta will be a value. What is the value? For example, if beta is about 60 degrees, 30 degrees, cosine of 30 degrees, what it will be the value, guys? A calculator?
1/2.
No, that is
0.5.
one. Nazanin say something.
Square root of 3/2, I think, right?
Yeah. 3 divided by 2, square root.
Square root of 3/2.
Yes.
Yeah.
It will be roughly about 0.8, something like that, if I'm not mistaken, something like that. So it means that the P nu of 0.8 should be equal to 0. This is what we are looking for. I mean, as an example. So these are the Legendre. Maybe I can run Mathematica if I can see that. So let me do that. Maybe I can have a Mathematica file and I can share the screen with you from a different platform. Legendre P, and it's Legendre of let's say 1 and 0 and x. Okay, that's a plot of this Legendre. Okay, I'm doing a screen sharing from a different platform, guys. Stop screen sharing here. I will come back to here. Stop here. Let me enter with another software, another one. Okay. Okay.
Recording in progress.
Okay. Okay. Yes, perfect. Share the screen. Go with Mathematica. You should see it now. Okay. So that's a Legendre polynomial. So just to give you a hint, I think the size is fine. If it's not fine, I can just change it a little bit. Let's go to 100. Okay, good. Let's go first with the Legendre P, Command F. So you can define in 2 forms, by the way, guys. As I say, that associated Legendre polynomial that we will be discussing about that is the second line. Oh, you don't see it. My apologies, guys. Put a question mark. So either you do you define it with 1 argument, an argument of x, and with 1 label of n, which is what we call it the Legendre polynomials, or you can go with 2 indices and 1 argument, which is n and m, which is an associated Legendre polynomial. We'll be discussing about the second one later on, okay? Let's go with the Legendre just to double check what we are doing. So Legendre of 0 and x, or let's say m and x, table, m changing from 0 and let's say 4. And those are the Legendre that we know very well. So it's 1x, 3x squared minus 1, and etc. So that's what we are expecting. Even we can plot them. I can take them, or let's say plot, evaluate what we have it up, or output of 5, and between interval of x and -1 and 1. Okay, so those are the Legendre polynomials that we do have. So the first one is 1, the second one, which is a linear, is x, the x power of 2, which is coming here, and the other one x power of 3 and x power of 4 with x power of 2 that we do have there. So that is very clear. Look here on, if you look at the positive side, you will see exactly at that point, Legendre number 4 is P4 is having a 0 value here. Here also another one, which is P3, which has a 0 value. Here P2 has a 0 value. Here P1 has a 0 value. P0 has never touches the x-axis, okay? The condition that you are asking is that I'm asking for Pn at the given value to be equal to 0. Not all Legendre polynomials, they will touch x-axis at that point. That's the reason that you are posing a condition and you are picking up the Legendre polynomial, which they have the zero value at that given point. So you are looking for that region, and any point is here, for example, 0.8, which is here, and you are asking which kind of Legendre polynomial there they have a 0 value. Okay, and remember, as I say, that not necessary that you are stuck with the Legendre polynomial of let's say integer quantity, which is m. And this case is m is changing from 0 to 4, but you can have also a real quantity. Let's say I'm just plotting another one, Legendre polynomial of 0.5. No, okay, not now. Do you see? Legendre polynomial of that one also has a value which is touching the axis. Let's say going with 1.5. So it's completely a different set of, let's say, honestly speaking, if I'm not mistaken, because that was really a long time ago, I wouldn't call them anymore polynomial. I will call them functions, because it's not integer anymore. It's a series that is not bounded. It's going, and it's look like Bessel function essentially. If you want to watch them, in a certain point, you can see that they have oscillation as well. So I will go with this language. So there are functions, not necessarily the index is an integer quantity, but is a real quantity. And you are looking for the values based on the condition that we had. We are looking for the values which that specific function is touching the x-axis at that given value or given angle that we are looking for. Is that clear, guys? If it's not clear, just shout to me, okay? I will try to explain it in a different way. Good? Let's do some fun things. Manipulate. I'm changing m for myself, and let's say change m from 0 to 10 with a step of 0.2. Do you see? Those are the functions that you are expecting. So anything may happen. So let me stop it and let's go with the even step of 0.5. I'm now, do you know what I'm doing right now? I'm looking at the Legendre polynomial of 0.1, 0.2, 0.3, 0.5, etc. until 10, and look at the values that you will get. Oh, let's do the plot range, just making it a little bit more, because I know that the plot range should be bounded by -1 and 1. Then you don't see the movement. Okay. Do you see? It's so funny. The 0 points appearing, and if I go higher, then even you may get the possibility to get multiple Legendre polynomial, which they have zeros exactly at the same point, right? So it may happen, let's say, P 10.1 and P 20.2, they have exactly 0 at 0.8. At 0.8, they are equal to 0. So look like this. For example, we can look for that one explicitly if you want. We can find it out. Do you see that the zeros are moving here? So I'm looking, for example, for 0.5. I would see how many of them they are touching that point. 1, 2, 3, 4, 5. So 5 of the Legendre polynomial in that domain, they are touching that region. Okay, so then the summation that we had will be only related to those Legendre polynomials. Good? Okay, stopping this. I will come back to our share. I hope that is clear now. Okay. Okay, so then from this condition that we have, which is that one, we are selecting the set of nu's, the set of those indices that they will give you 0 values at that region. So then, therefore, we have the solution now, which is summation on nu k, or if I want to be careful, this is not really summation because it should be integral, it's a continuous variable, but I will put it in a different way. I will put it as k, right? And I would say that nu's are now labeled by k because it can be one of the Legendre, another Legendre, another one, and another one. I will label all of them with a k, and it will be r power of nu k, p nu k of cosine of beta, cosine of theta. And that is the potential that I have.
Sorry.
Yes.
Do we know that these K1s are finite? Or they can be like, there can be infinite number of Legendre functions that can have same zeros?
I would say that is infinite number.
Okay.
It's not bounded. It's not bounded. Yes, you're totally right. So it's an important point that the series is not limited. The series goes really to infinity.
Thank you.
Because if you look at the expression, if you look at the simulation, actually, you will see that is oscillating, right? And anytime that you add it, you will see that there is look like an oscillation, like a sine function, which the frequency is changing. So how many times is happening? I would say that infinite. It can be a mathematical proof. I'm sure that people, they have already proved that, but mathematically proving that there is an infinite number of Legendre polynomials and Legendre functions, which they will give a 0 value at a given point. Okay, I'm sure that mathematically has been proven there. Oh, people, they can prove it by contradiction. So just saying that we assume that we have a bounded one, but then you can add another one, which is more than that. So, and remember, nu k are the set of the index of Legendre functions, which they give 0 value at cosine of beta equal to as cosine of beta. Okay. Recall, nu k is integer, but nu k is not integer. Good. Now, also I can find electric field now. Take the derivative, you will find the electric field. And you can find also the charge densities if you wish. Even if the surface is kept at a certain potential, is exactly the same situation. The only things that happens is that the point that you are looking for touching the 0 axis now is moved. Let's say I'm keeping that cone in a given potential of V0. V0 will be a normalized one, which will go away. So you will have a certain value which is touching the axis. How many times this oscillation function is touching a certain point? So anyway, that can be translated in different let's say languages if someone is interested. Clear? And if you look at inside of your book right now, I'm looking at your book, and I see that in your book also that has been expanded in terms of hypergeometric functions, which is very interesting. Hypergeometric 2f1. And so essentially, which is very interesting, by the way, also the hypergeometric. So just to introduce you to what is the concept, essentially that can be any series that you do have it, which they go with certain arithmetic, then they can be expanded in terms of a function which they call it hypergeometric. And usually hypergeometric, they are labeled by 2 indices, guys. So is FQP or PQ is up to you of, let's say, certain values here, another certain values here, and an argument. The number of values that you do have here, they are Q numbers, and the number of values that you have it here is P values. For example, 2f1 of, let's say, A, B, and the one will be C and Z. So you have 2 parameters here, you have 1 parameter here. If I have 3f5, means that I have A, B, C, D, E, F, G, H, and Z. What are they? So I have 5, let's say, parameters here, and I have 3 parameters here. What are the meaning of those? So essentially, they are series, which they start always from 1, all of them, and then it starts from A, which is the first 2 arguments, they will be on the numerator, AB, and the other argument will be in denominator, which will be C, multiplied by Z divided by 1 factorial, plus A times A plus 1, B times B plus 1, divided by C times C plus 1, Z power of 2 divided by 2 factorial, etc. Whatever you have it in the denominator, they appear as a sequence, and you have to change them by an integer quantity and multiplying it. Okay, and what happens in the denominator will be in the second, let's say, second label that you do have, and appears in the denominator as well. Okay, so it's a useful function, and 1f1 is linked to Bessel function, if I'm not wrong. 2f1 can be linked to Legendre, can be linked to Legendre polynomial, can be linked to the Bessel function as well. So it's very, very complicated one. So is a general function, and mathematics also has it inside, that you can express some, let's say, solution of differential equations to it. Okay. So inside of your book, they say that Legendre polynomial, Legendre function of nu of x, when nu is not integer, of course, is given by 2f1, which is a hypergeometric function of 2f1 of minus nu and nu plus 1, which is the two indices, the first one that appears in the denominator, and then you have 1, which appears in the denominator, and then you have 1 minus x divided by 2. Okay, so that's a built-in function in Mathematica that you can use it, or even MATLAB, I'm sure that it has it. So how, if for any reasons, if your software doesn't have the Legendre function, you can introduce Legendre function by using the hypergeometric function. Okay, this is something that it should be noted in your calculations. Okay, fantastic. Do you have any questions so far? Clear? Now let's go back to Laplace equation in the spherical coordinate. Whatever we solve for m equal to 0. Right? We did not touch what is going on with m that is not equal to 0. So indeed, the radial part was given by r power of L, or 1 divided by r power of L plus 1. The radial part was clear. The azimuthal part was e power of im phi plus minus. The radial, the theta part, we say that the theta part when m is equal to 0, which means that also that term will be equal to 1, that is given by PL of cosine of theta. What happens when m is not equal to 0? How to handle this? Which means that the radial part again is r power of L, the other one is r power of L plus 1, and we have e power of im phi, but we have to find a solution for the theta, which was the differential equation that we had, which was d dx of 1 minus x squared d dx of theta plus L times L plus 1 minus m squared divided by 1 minus x squared, theta equal to 0. Remember, that was the differential equation that we had. And we assumed that m is equal to 0 because it was easier to handle. Again, this differential equation can be solved with the Frobenius technique. And doing the expansions around m equal to 0, x equal to 0. I don't want to do these expansions. What happens that the solution will be what they call it associate Legendre polynomial. Still, the solution will be polynomials, guys. Okay, is not infinite numbers. Is not look like what we had previously, which was a non-integer quantity. Here is a polynomial. And what I want to say is a polynomial that we call it associated Legendre polynomial. And it will be labeled by two indices. Again, the same fashion that we had, it was labeled by PL of cosine of theta. But now you have another index, which is m. And in order first of all, remember that the same fashion, if you do the expansions, then at x equal to 1 and x equal to -1, then still the series should be converging. Applying this condition will tell you that L is a positive integer. And now we have another condition on M as well, that M is belonging to -L to L. Okay. Now, also, due to having the series to be converging, okay, let me go from the beginning again once more, because maybe we have too many information here. These differential equations should be solved, right? How can we solve it? Frobenius technique. Theta will be expanded as x power of alpha, summation of an, x power of n. And we know that we did the expansion around x equal to 0, and we know that this series should be bounded for x plus -1 as well. If we have this bound, then we have a condition on the series to be also truncated. In order to have the series to be truncated, both L and M must be integers. L is changing from 0, 1, 2, and any values, but M is bounded by -L to L. Okay. Now, due to azimuthal dependency that we do have, we have another index which is playing the role here. So indeed, for the Laplace equation, we do have these following solution: AL and M, of course, R power of L plus BL and M, R power of L plus 1. Then we do have E power of I M phi. We do have PLM of cosine of theta. And we do have two summations. The first summation will be on L, which is changing from 0 to infinity. And the second summation will be on M, which is changing from -L to L. Okay? Previously, we had only this term without M. So M, it was 0 here. Now, the azimuthal direction also plays role, and then we have to go with this expression, which is theta dependency, M is there, and the L phi is there, and also R is there. Okay? That's a general solution that we can work with it, and we can find potential in the space, and that will be extremely useful, by the way, for our calculation that we will be using during next lecture. There is something new here as well, which we have to be very careful and handle it properly. This part, let's go with another color. This part only depends on the R, right? Depends on the radial distance. What about this part? Assuming that you are inside of a sphere and you want to address point by point what is going on in the sphere. How many parameters do you need? two parameters, theta and phi, because the surface of the sphere is a bound for you. Here, the same situation. You have theta and phi dependency. This is what we call it solid angle, right? So it does not define the distances, it defines the angles, the solid angles, or the position in the space. So these functions, these two functions together, they are really, really important. And we will be discussing about that in next 15 minutes, okay? Before going there, I have not talked about PLM of cosine of theta, or in general, PLM of x, which is associated Legendre polynomial. Remember, it's polynomials. Okay. Again, you can go to Mathematica. You can have it, which with the function which is Legendre P, and it will be labeled by L and M and X. That's the function that you can use it in Mathematica. So PLM of x can be driven from the Legendre polynomials that we previously introduced, from 1x, 3x power of 2 minus 1 divided by 2, and other terms. And the expression that you can get it from them, which I don't memorize them, by the way, I'm cheating right now, I'm looking at the paper, is given by PLM of x is given by minus 1 power of m, 1 minus x squared, m divided by 2, okay? M derivative of Legendre polynomial of L. Look, what is happening is that you know the Legendre polynomial. We already built it up, right? You take the m derivative of this. You take the derivative m times with respect to x, and then you multiply it by minus 1 power of m, 1 minus x squared power of m divided by 2. And then what you will get associated Legendre polynomial. Is this a polynomial? Yes. The derivative also will be polynomial. Is multiplied by another polynomial. So that's the reason that I call is associated Legendre polynomial. Okay. That is for positive m value. If you look at the relation between, and that's given for any m value, but if you look at the relation between negative m of x and what is going on with PLM of x, the relation is given by minus 1, yes, minus 1 L minus m factorial divided by L plus m factorial. So remember, L can take any positive integer quantity, m can take minus L to L. For example, if you have a L equal to 2, m cannot take 3, right? So P2 0 exists, P2 1 exists, P2 2 exists, P2 3 no, okay, or is 0 if you want to talk about that. And then from the other side, of course, we have 2p minus 1 to minus 2 as well. And the relation is given by the above expression. Associated Legendre polynomial also, they are orthogonal functions. But with respect to which index, guys? They are not orthogonal in M, they are orthogonal in L. So integral of dx, the weight is 1, by the way. There's no need to discuss, but I'm telling. So PLM of x p l prime m of x. Remember, these index is the same. From -1 to +1, that will be given by 2 divided by 2l plus 1, which we knew about that. And then there will be only one coefficient which is appearing here, which is l plus m factorial divided by l minus m factorial, delta of l and l prime. Good. So Legendre polynomial, which they have 2 indices, one of the indexes is important for us, and we have to take care, is the lower index or the first index. They are orthogonal with respect to that index. Okay? You may ask me what is happening with the m, if it's m and m prime. I will tell you. Okay? Is that clear, guys? I'm not expecting you to memorize what is going on with P22. I don't do that even myself. If it's needed, I will give you the expression so you can use it. So what is important is you have to know the logic, how to building up them. Of course, the relationship, of which is a Rodriguez expression, can be given to you, and you can use it in your exam or in your research activity. I'm assuming that there are many books about the Legendre polynomial. So people, they are writing books about the property of these functions. Anyway, so now let's go back to the azimuthal and the theta part of our expansion, which we call this the solid angle part of the expansion. This is orthogonal with respect to theta, right? Or the index of L. This is harmonic oscillators, right? They are orthogonal with respect to phi or m, if you want to watch it in a different way. So let's build up another function, which we call them YLM of theta and phi. And we call these spherical harmonics. First of all, it is in spherical coordinate. It depends on the theta and phi. That's the reason they call it spherical. And why they call it harmonics? Because of this first term. Is the ideology that they got it from the harmonic oscillators, which they form complete basis, the Fourier expansion that you do have. Okay, so PLM cosine of theta e power of I and phi, they form complete basis in the with respect to theta and phi, okay, or in the theta and phi space. I will add 2 coefficients here just to make it normalized. Okay, let's do that. And then normalization is coming from the fact that we previously also introduced the Legendre polynomial that mathematicians, they use it. And I will consider also these an associate Legendre polynomial. So let me do the expansions. And first of all, I have to move this part because it's too close. Okay. So that will be square root of 2l plus 1, which is not coming as a surprise because we knew previously that is the coefficient that you needed for normalization, divided by 2. And then you have another one, which is l minus m factorial divided by l plus m factorial. I think that should not be 2, that should be 4 pi, because I need another one divided by square root of, if you recall that one, in order to have a normalization, it should be 1 divided by square root of 2 pi. So that should be 4 pi. Okay. I call these spherical harmonics. They form complete basis in theta, in both, remember, theta and phi. Each of these functions, what I have done, these function and these function, both of them, they form complete basis in phi and theta. Both of them together, they form a complete basis in both theta and phi. And that's very, very important because you can use it in quantum mechanics, you can use it in electrodynamics, you can use it in classical dynamics. Anytime that you want to do an expansion in spherical harmonics, spherical coordinates, you need them. Okay? Perfect. So what is the relationship between them? First of all, you have to know the measure that you do have. What are the measures that we are using? First of the first one is the integral is d phi. The second one is d of cosine of theta. We multiply these together and I call this d omega is my measure, which is not surprising. It will be sine of theta, d theta, d phi, which is the solid angle essentially that we are looking for.
Shouldn't we also have like a squared somewhere, like a
A squared?
like a r squared?
No, this is independent. There's no functionality of R. This is only related to how do you see a sphere.
Okay.
There's no R. There's no R at all. R is here. Okay, is only related to the solid angle. So let me give an example. Are you in art building? Okay, you are in art building. You look at the window. You look at the window, or you look at the building at the front of the window. In order to describe both of them, you need the same theta and phi. R will be different for them. We are only talking about the solid angle. We are not talking about the rest, okay? R is completely different scenario. We will be discussing about that, or you have seen the R, right? Is that clear, guys? Any problem? Okay, so now the measure that you do have, or let's say the elements that you do have is d phi, d cosine of theta, which both of them, I call them the solid angle of d omega. What is integral of d omega? When I say integral of d omega means that on the entire the space. So integral of d phi, d cosine of theta, when theta is changing from 0 to pi, and phi is changing from 0 to 2 pi. That should be 4 pi. Right? This is how do you see a sphere. The entire the sphere is 4 pi steradian. Okay? Is that clear, guys? Perfect. So now I will say that integral of YLM theta and phi, YLM prime, both of them, theta and phi, d omega, one of them definitely needs a star, that is equal to delta of LL prime, delta of M prime. Now, with YLM, I built up a function which they are orthogonal in both M and L. Okay? And also they are complete basis because harmonic, which is e power of Im phi, is complete, and PLM cosine of theta also is complete. So multiplying these two together, now I'm expanding, let's say, one-dimensional space of theta or phi to a two-dimensional surface, which is theta and phi together. And now I'm building up a function which is orthogonal and complete basis and describing the entire sphere, surface of a sphere. Okay, so I think I promise Tarek that I will finish it here. So I will finish here. Tarek, next lecture, I will be discussing about the property of YLMs, and then we will go to multiple expansions, and I will do also the green function expansion. You have to understand why we are doing these headaches to ourselves, because we are going to use it to find the green functions. We are using them to understand what's going on with let's say, charge distribution and understanding the contribution of each charges. Okay, so I will stop here. And I will see you next lecture. I will stop